Okay, so I think I'm all set. Thank you so much for the introduction. Thanks everyone for coming today. Really happy to be a part of this workshop. The previous two talks, I think, set a little bit of a high standard. Those were both fantastic. I don't do quite as much experiments, so I'm not going to have as many videos for you, but I promise you there will be one nice video-ish at the end. So if you tough it out, we'll get there. So our group works on and thinks a lot about how learning and dynamics and control can interact together to allow you to kind of get the best of all worlds. And we think about this in the context of autonomy. Learning is now really becoming an unavoidable part of the autonomy stack, right? We know that learning is essential to get vision-based algorithms to work well. And as the previous talks and other talks in the conference have shown us, learning is also starting to come for lower layer stuff as well, right? So planning and control and things like that. So in the context of safe autonomy, which is the topic of this workshop, I think we've all seen videos of robots falling over, Teslas crashing into things that they shouldn't, things like that. So I don't think I need to motivate the importance of safe learning and control in the context of robotics and autonomy. So I'm going to try to motivate things from a different perspective that maybe speaks a little bit more to some of the pains that graduate students in the audience might have to deal with on a daily basis, especially those who work in deep learning and deep reinforcement learning in particular. I mean, I think we all know that this is deep learning and deep RL can be very, very fickle. Right, so if you have some new algorithm that you want to try out and you want to get your humanoid or your half cheetah to do something interesting, you have to fight with a lot of hyperparameter tuning. And sometimes things just don't work, and you'll be staring at these different training curves, and they're just not going to go where you want. Where after a week of staring at these things, you're actually going to start having like deep nightmares about training curves. I got these off of a blog post that I think Andrzej Karpathy hosts on Tumblr, where people actually submit in their wonky looking trading curves. And so the question is why is this happening? All good. Okay. I wanted to make sure that wasn't me with feedback. Okay. So the question is why isn't it working, right? I mean, so that was dramatic. So the question becomes then, is it that I just haven't experimented enough and my learning rate isn't fast enough, or my cosine schedule is decaying too quickly, or my network architecture isn't the right one? Maybe I need more skip connections. I mean, that's one possibility, right? And if I fight with this some more, collect some more data, then maybe I'll get something good out of it. Then the other possibility is that the problem that I'm working on might just be fundamentally hard. It might just be that no matter what I throw at this, it's not going to behave well and it's not going to behave reliably. There we go. And so, unfortunately, right now, we don't really have a systematic way of teasing these two situations apart. And what I want to talk to you about today is some of the work that we've been thinking about in terms of how to tease these things apart. And to do that, I want to take inspiration from an area that I'm quite familiar with, which is robust control. So if you go back 30, 40 years, and in particular, prior to the advent of modern control, people would actually face similar types of problems where they would be tuning a loop at a time, checking that each loop individually worked well, and then hope that the whole thing would work. And so I know that a lot of people, when they hear robust control, they immediately think H-infinity control, complicated math. I don't like this. But arguably, one of the most practically important consequences of the whole robust control area is the identification of fundamental limits, identifying that there are just some systems for which all controllers, no matter what I do, are going to lead to just bad performance. And so a really nice example that you can actually try at home if you have an extendable pointer, like an old school one, is this idea of trying to balance an inverted pendulum in your hand using vision. We can look at this problem and analyze it from a control theoretic perspective and actually characterize the hardness or the fragility of this problem. So we can show that if the length of this stick gets shorter, this becomes a quantitatively harder control problem. And this is due to the unstable pole getting worse. In fact, we can make this even worse if we allow for a long stick, but then let's say put a baseball cap on or something, so I can only look at halfway through the stick. This introduces an unstable zero that's very close to the unstable pole, and in essence results into a near loss of controllability. So things become really almost impossible. And you can try this at home and you'll see that this is in fact the case. And so the major takeaway here in this context is that it says that I need to change the system. That if my fundamental limits tell me that nothing good can happen no matter what, then I need to change something about my problem. In this context, this idea of looking halfway through, it's an analog for just having crappy sensors. So for this system, I would need better sensors to resolve this, to improve these fundamental limits. Okay, so what we want to do is take this same philosophy and bring it over to thinking about learning for safe control. And this particular question that we want to answer is, what makes learning controllers from dynamic data either easy or hard? And so the informal meta theorem that we've been converging towards is in some sense something that you would hope to see, which is that if there is a good controller lurking somewhere underneath the hood, then it should be pretty easy to find it. And similarly, bad controllers, controllers that lead to bad performance, they're going to be really hard to learn. So if you find yourself in a situation where you're training and things are just kind of going all over the place, it may be that you're in this latter situation. All right, so for the rest of the talk, we're going to split things up into two sections. We're going to first start with a little bit of a pessimistic perspective and try to understand what makes learning controllers hard. Over the last 5 years or so, we've gotten a really good understanding of what learning to control looks like in the context of linear systems. And we've had a lot of positive results. And I'm going to show you that even though we have these positive results, some of them are a little sneaky in the sense that they're hiding some factors in there that could actually get you into trouble. And then we'll actually see that there are some linear systems that are hard to learn to control, and I'll try to convey some physical intuition as to why this can actually happen, and why as roboticists you might care about this. Then we'll switch gears and talk about what makes learning controllers easy. And we're going to try to think about problems in the context of nonlinear control here. Now, I'm not claiming that we've solved the full-blown nonlinear reinforcement learning problem. In fact, we're not going to talk about RL, we're going to use imitation learning as a case study. And we'll show that certain underlying ideas related to nonlinear robust stability actually give you a very clear understanding of when, why, and how imitation learning works. And then we'll wrap things up. Okay, so let's set the stage for learning to control linear systems. Our system dynamics are going to be described by the kind of standard LTI setup. I have a system state X. I have my autonomous dynamics described by my matrix A. My control input U is going to come in through my matrix B, and then there's some exogenous process noise or disturbance that I need to do. Right, and the goal here is to regulate my state to 0. We're also going to study the linear quadratic regulator, or LQR optimal control problem, which can be written compactly in this form. This is the cost function that I want to minimize. The math isn't super important. The idea here is I want to minimize some steady state variance of a weighted sum of the state and the control. So I want to minimize the energy that's transferred from the disturbance to my state, as well as the amount of control input energy I need to use to do that. Now, I know linear systems are not particularly interesting from a robotics perspective. Nothing you all do is linear, but I'm still going to argue that linear systems and LQR serve as useful benchmarks. They're simple and tractable enough to analyze, but they still capture some fundamental rich properties of dynamical systems, and in this context, learning over dynamical systems. Okay, so I promised you that I would unveil some of the sneaky hidden factors behind what makes learning to control linear systems easy. So let me pose 2 specific tasks. We're going to think about 2 different tasks. One is an offline task where I have an unknown system, and I just want to learn how to stabilize it. Right, so I'm given some unknown linear system. I don't know A and B here. I get to run some experiments, and my goal is to find just a static feedback matrix K so that the closed loop system is stable. And we have a good understanding of when and how this works. Lots of different results have shown that if I collect a polynomial number of experiments or data points in the size of my system, then I can synthesize such a controller, and this will hold with high probability. Now, this C-sys stabilization here is some constant that depends on the underlying properties of my system. We can also talk about an online task, and we're going to characterize this in terms of regret bound. So here, just think adaptive control. The goal here is given, again, an unknown system, I don't know A or B, I want to compute a controller that minimizes this running sum between the cost that I incur and what I would have, the optimal cost I would have been able to achieve had I known the true A and B matrix. So the difference between this online task and the offline task is in this adaptive setting, I actually have to do a little bit of exploration. I have to improve my estimates of the model as I go. And again, we have a very good understanding about this problem, and we can show that this regret bound scales at a rate like square root t and polynomially in the dimension of the system. So this tells you that at my learned controller here, if I do the right thing, will converge to the optimal one at a rate like 1 over square root t, so fairly quickly. Okay, so this seems to suggest that learning to control linear systems is easy, but is it really though? So I'm going to pick on one of my results where we show that if I want to do something like a least squares estimation and do some robust control, then I need to collect about n plus p, n is my state dimension, p my control input dimension, divided by the minimum singular value of the controllability gradient of my system. That's how much data I need to get a stabilizing controller. And we have a similar type bound for regret bounds that also scales in this nice polynomial way. And I have this other term in front that corresponds to the size of the algebraic Riccati equation solution. Now, I want to highlight these two things in red here. These are those system-dependent constants that I mentioned earlier. There's an implicit assumption here that these things are not hurting you. They're not big, right? So, what are these terms hiding? Can these things actually get me into trouble? Right? And so it turns out that for certain systems, these things can actually be really, really bad. And they can lead to exponential blowups in the amount of data that you need to compute, that you need to collect. So I want to give you an example of a linear system that can be hard to learn to stabilize. And I want to set the stage in terms of the kinds of systems we're going to look at. We're going to characterize the controllability of a system in terms of this controllability index kappa. And this is basically the amount of time steps it takes to take the system state from one state to another. Right, so if I have, let's say, a fully actuated system, then this will be 1. If I have a double integrator, this will be 2. If I have an n-chain integrator, this will be n. Right? Right. And then we have this other kind of condition here, which is just we're bounding our systems away from control, from not being controllable. So I could always build a system that's arbitrarily close to being not controllable. That's not interesting. What this is saying is that at the very least, I have to perturb my system, my matrices by something of size mu to make my thing uncontrollable. Another way of thinking about this is each of my individual states have at least mu coupling to their neighbors. And so what we can show is that the complexity of learning a stabilizing controller is in fact exponential in this controllability index. Right? So if this controllability index scales with the dimension of your system, so let's say I have a chain of n integrators, this can get me into a lot of trouble. So I want to give you an example of what these kinds of hard instances look like. So consider two systems that I have to try to determine which one I'm dealing with. It consists of one marginally stable mode at the top here. And the only way that I can actuate it, that I can actually control and stabilize this top mode, is through this chain of damped integrators that are damped via this parameter mu. Now, if you stare at this long enough, you should be able to convince yourself that the only way to actually stabilize this thing is if I'm able to identify the sign of that top parameter plus or minus. I basically have to pick my controller to cancel it out. So this tells me that if I want to stabilize this thing, I actually have to identify what sign this term is. But this is actually a really hard problem because any excitation, anything that I inject into my system to try to tease out what this parameter value is, gets damped by mu to the n minus 1, right? So this can be very, very small. And so this is what translates into this exponential sample complexity. So the main takeaway here is that if I have unstable modes that are only controllable via some system identification bottleneck that has low excitation, then this can lead to a hard stabilization problem. Right? And so this is a simple example with zeros on the diagonal, but you can have non-zeros on the diagonal too. Another way of saying this is if I have a chain of, if the only way that I can actually actuate my system is through a chain of damped integrators, then I might be in trouble. So, those of you who work on underactuated robots, soft robotics, if I, let's say, discretize a PDE, they all look kind of like this, right? So even though this is a toy example, we do believe that this is actually representative of some physical systems and something that you need to worry about. And I'll also just add, and I'm not going to go into much less detail here, that the regret analog of these things is also, you can also show that it's hard under pretty much the same setup, except what's interesting here is that it's a different condition that gets you into trouble. And in particular is if I have some modes that are too easy to excite, then this can lead to large regret. And this has to do with the fact that I actually have to explicitly explore to identify my system. So in this case, the way to think about this is if I have a chain of integrators that don't damp the input, then this can also lead to trouble. Okay, so thank you for bearing with me on the theory side of things. we can kind of zoom out and summarize what we showed, which was that systems that are either too excitable or not excitable enough can have controllers that are really hard to learn. So the question now becomes, what makes learning controllers easy, right? We want to kind of go to the flip side. And so, as I mentioned, we're going to think about this in the context of imitation learning. Just to make sure that we're all on the same page here in terms of what imitation learning actually is. The idea here is I have some expert policy, some expert controller that I want to learn to imitate. This could be something that's like computationally expensive, like nonlinear NPC. It could be a human operator or something like that. And what I'm going to do is run a bunch of experiments to collect some data. And this data will consist of actual state trajectories as well as labeled values of the input that my expert would apply on those state trajectories. I'll then run a regression problem, basically just supervised learning to try to get an estimate of the policy pi. And then I deploy this on my system. In the simplest version, kind of vanilla behavior cloning, that's it. And then you just kind of hope for the best. More sophisticated versions maybe close the loop and do something a little bit more interesting. Now, the challenge here is that you have this problem of distribution shift that leads to imitation learning to fail. And so rather than going into math, let's just look at this from a kind of cartoonish picture, where suppose that this is my data set of or distribution of expert trajectories. And suppose that I'm now trying a testing out my learn policy, starting at this black line. Now my expert policy would follow this blue arrow, but because my learn policy is going to have a small error in it, I'm going to follow this red arrow and end up over here. Now I'm still okay because I'm within my training distribution, so my expert knows what to do, and I only make a small error again. But now this kind of compounding effect of errors has kicked me outside of my training distribution. So again, whereas my expert knows what to do, I've not seen this data in training before. So I'm going to make a bigger error, which gets me even farther out of my training distribution. And while my expert knows what to do, I have no idea what to do at this point because I haven't seen this during training, and things blow up. So what we want to understand here is how do the underlying stability, safety, and smoothness, nice properties of the expert affect the sample complexity of imitation learning? How do we prevent this from happening? So I think it's important to give context here in the sense that this is a well understood phenomenon. Everybody who's ever tried to do imitation learning knows that the vanilla behavior cloning approach is sensitive to this idea of compounding errors. So folks in imitation learning have proposed two variants of ways of dealing with this. One common one is called Dagger, which is an on-policy approach, which basically allows your expert policy to correct the errors made by your learn policy, and you mix this into your data set to help improve the performance. And then off-policy methods, things like Dart, which is some really nice work out of Berkeley, and Gale, that uses generative adversarial ideas, they try to do data augmentation. So they inject noise during training to kind of spread out the expert distribution and preemptively capture the errors that your policy is going to make. And both Dagger and Dart and Gale, they all work really well when you can actually deploy them. So what we wanted to try to understand was what's going on here? What fundamental nonlinear control phenomenon explains why this actually works? So the key idea here, as I said, is to show learn policies how to recover from errors, but there's an implicit assumption here, right? Which is that my experts actually know how to recover from errors. Right? Nobody actually comes out and makes this explicit, so that's what we're going to do. We're going to make explicit the assumption that the underlying expert is robust to errors and can recover from them, and try to understand how this manifests itself in imitation learning. So why is robust stability important? So we're going to study this question in the context of just a deterministic nonlinear system. And we're going to look at the evolution of this system under an input composed of two components. One is the test policy that I actually want to analyze, and one is this delta term here, which is going to characterize an input perturbation. Later, we're going to use this to capture the error of my learn policy, but for now, just think of it as as any input perturbation. Now, the imitation gap, the thing that I want to keep small, is I want to make sure that the trajectories generated by my test policy, that they stay close by to the experts generated by my expert policy, right? That's the whole goal of imitation learning. And our approach here is going to be to view test policies as perturbed experts. So in particular, if I look at my test policy, I can rewrite it as my expert policy plus the mismatch between the two, right? I'm not doing anything super sophisticated. I'm just adding pi star minus pi star. And so this allows me to rewrite the imitation gap as the difference between a perturbed expert trajectory, and a nominal expert trajectory. Right. So this idea of making sure that perturbed and nominal trajectories stay close by to each other is a well-studied notion in nonlinear control. In particular, it's this notion known as incremental input to state stability. I don't know if Aaron is still watching or not, but this slide's for you. I didn't want you to yell at me for not including the math, but more importantly, what incremental input to state stability captures is this idea that trajectories behave similarly to each other over time, even in the face of inputs. So the first condition says that I'm going to forget my initial conditions. So if I start at different initial conditions, trajectories converge towards each other. And the second one, which is really the one that we're going to use, is that bounded disturbances have bounded effects. And we can really characterize all of these different rates of convergence and boundedness things in terms of these comparison functions, these class K and class KL functions. So with this in mind, if we apply this perspective, if we assume that our underlying expert leads to an incremental input to state stable system, then we can actually bound our imitation gap in terms of this perturbation. Okay, so we've made some progress. Let's see what we can do with this. So I'm just recopying what I had at the bottom of the previous slide. And what we're showing here is that we can bound our imitation gap, the imitation learning error, in terms of some function gamma that captures the robustness of my expert and the policy mismatch under my test policy pi. Now, the problem is I don't know how to actually give you any guarantees on this policy mismatch under the test policy pi, because at training, I only get expert trajectories. So we're going to do something really simple. We're just going to take Taylor series expansion. So I'm going to take my policy mismatch under my test policy pi, upper bound it by this Taylor series expansion about my expert trajectories. So I have my policy mismatch under my expert. I have now the Jacobian of my policy expert under my policy mismatch under my expert. And then this imitation gap shows up on the right again. So on the one hand, we've made a lot of progress here because I can use just standard statistical learning theoretic techniques to bound these policy mismatch terms that are underlined in blue. On the other hand, though, this imitation gap, which is the thing that I'm really interested in bounding, it appears both on the left-hand side and the right-hand side if I chain these two inequalities together. So I end up with this implicit inequality. So how do I deal with this? Well, it turns out that this suggests that if I match not only the policy, but also its higher order derivatives, then I can actually invert this bound and get something reasonable. And so this motivated us to propose this idea of Tassel or Taylor series imitation learning, which says that if I want to ensure robustness to distribution shift, then I actually need to make sure that my learned policy matches the expert, not just in the output, but in the first P terms of the Taylor series. Okay. And this P term here, the order P is really determined by the scaling, the underlying stability properties of my expert. So we can define a general version of this, but if I want to make things a little bit more concrete, if I assume that this robustness property decays very quickly, so let's say quadratically, then we can actually show that behavior cloning, just as is, will work. But this is a very strong assumption that I actually don't even know how to cook up. So I actually don't know of any real systems that aren't artificially cooked up that satisfy this. In contrast, if I assume a linear decay, and this we can prove using standard Lyapunov techniques for systems of interest, then you have to not just do behavior cloning, but what I like to call Jacobian cloning as well. Right? And so you show then that if we do that, we can kind of turn this nice learning theoretic crank to show that we will have small imitation gap on a new test initial condition with high probability if I collect enough data, where enough data is again determined by the underlying stability property. So the more stable my system is, the less data I need to ensure generalization. Okay. So we tried this out on Mujoko. We took experts from stable baselines. And what's cool about this is you saw there's nothing super complicated about how you can implement this. Take your favorite imitation learning algorithm and just add a Jacobian loss to it. And what this is showing you here is that it just makes it work way better right away. So at the top row, we're comparing behavior cloning with and without our tassel loss. The middle row, Dart with and without our tassel loss. And the bottom row, Dagger with and without our tassel loss. And these dashed lines are the ones that are with the Jacobian term. And you can see that in all cases, this leads to a dramatic improvement. And the harder the problem, the more dramatic the improvement. And so I'll just end with a video to kind of show you what this actually looks like in practice. So up top, we're showing the behavior of behavior cloning, and at the bottom, the behavior of the Jacobian augmented loss, where we just use 12 training trajectories. And so you can see up top already, the ant and the half cheetah have completely crashed over. The humanoid broke as well. And eventually the walker 2D will fall too. Our humanoid also falls, just to show that we're not cheating here. We just kind of picked some random experiments for the video, but it lasts way longer. So I know I'm running out of time, so I'm done here. So, if we can zoom back out and think about this meta theorem, what we've shown is that controllers that are incrementally robustly stable, they're easy to learn. And if we kind of bring back our other idea, if systems have these modes that are either too excitable or not excitable enough, they can get you into trouble. So let me just end by thanking my amazing collaborators. The first half of this work was led by Tassos Tsiamis, who's now a postdoc at ETH, did his PhD at Penn. Ingvar Zeman from KTH, who's going to be joining my group as a postdoc shortly. And then the second half was led by an amazing undergrad from Penn, Daniel Frommer, who's starting his PhD at MIT in the fall, and my student Thomas Zhang, and some of my fantastic collaborators from Google as well. So I'll end there. Thank you all for your time. I'm really sorry I went a little bit over time. And if there's time for questions, happy to take them.